Today we are going to explore production RAG systems from a complete architectural perspective and cover everything from document ingestion through to serving answers at scale. We'll cover four major areas. So, number one, document processing and intelligent chunking strategies. Number two, vector databases and how they scale to millions of documents. Number three, hybrid retrieval that combines multiple search approaches. And number four, caching architectures that can dramatically reduce your operational cost. By the end of this video, we'll have a complete understanding of the architectural decisions, trade-offs, and optimization strategies that make RAG systems work much more effectively in production environments. So let's get started. Let me first start by framing the architecture challenge that we are addressing here today. RAG systems face fundamentally different constraints at production scale compared to initial implementations. The architecture requirements diverge significantly across several dimensions. Initial implementations typically handle limited document sets with straightforward retrieval patterns. They are excellent for validating concepts and understanding the technology. However, production systems must serve millions of documents while processing thousands of concurrent queries. They need to maintain sub 3-second latency at scale and optimize carefully for cost efficiency across API calls and infrastructure. This architecture evolution requires systematic optimization across every layer: document processing, retrieval strategies, caching, and monitoring infrastructure. Each of these components need careful design and tuning based on your specific workload characteristics. Today, will explore a complete production architecture that addresses these challenges with proven patterns, quantifiable trade-offs, and practical implementation guidance. The patterns I will share here, they come from real production deployments. Through your specific requirements will determine which optimization provide the best return on investment for your system. Now, let me show you the complete system architecture that we are building here today. The production architecture integrates several sophisticated components working together. It includes intelligent caching that can reduce cost by up to 70 to 80% in workloads where users ask similar questions repeatedly, something like a FAQ style workloads. Now, I want to emphasize that these results vary significantly based on your query distribution. If your application handles unique research queries where each question is different, your cache hit rate might only be 10 to 20%, and the savings would be proportionally lower. The system employs a hybrid retrieval combining vector search with keyword search. It uses re-ranking that typically improves the accuracy by 20 to 30%, though this depends on your baseline retrieval quality. If your initial retrieval is already strong, you might see smaller gains. If it's weaker, you might see larger improvements. The system uses streaming responses for improved perceived latency and is designed for horizontal scaling across both compute and storage layers. Performance characteristics depend heavily on several factors: your specific query patterns, your hardware configuration, the characteristics of your document corpus, and which optimization strategies you end up implementing. The architecture I'll show you here supports linear scaling through component replication and intelligent sharding strategies. Now let's dive into each of the components, starting with the document processing. So document processing establishes the quality foundation for your entire retrieval system. The approach you take to chunking directly impacts your everything downstream. Fixed size chunking with arbitrary boundaries faces some real challenges in maintaining semantic coherence. When you split document without considering their structure, context boundaries may split mid-sentence, mid-paragraph, or even mid-code block. This fragmentation reduces the retrieval precision because the chunks lack complete semantic context. The structural-aware recursive chunking takes a different approach by respecting document semantics. The algorithm should prioritize document-level boundaries like chapters and sections first. Then it should split by paragraphs, and it should only split sentences when paragraphs exceed your size constraints. The key insight here is that different document types have different structural requirements. For technical documentation, you should preserve code blocks intact because splitting code samples destroy their meaning. For legal documents, you should maintain contractual clauses together because legal interpretation depends on complete clause context. For research papers, you should keep the citation context together so references they remain meaningful. The document structure carries semantic meaning that authors have intentionally embedded. Your chunking strategy should leverage that structure rather than completely ignoring it. This is one of those foundational decisions that has ripple effects throughout your entire system. Now let me walk you through how the recursive chunking algorithms operates. The algorithm works top down through document structure. It attempts the splitting by major document boundaries first, like chapters and sections. Then it checks if the resulting chunks fall within your target range of 300 to 800 tokens. If the chunks fit within these bounds, you store them. If the chunks exceed the upper limit, you recursively split by next structure level down. This approach maintains semantic coherence throughout your corpus. Concepts and explanation remain together rather than being fragmented across artificial boundaries. For example, a complete explanation of database indexing strategies stay intact instead of being split mid-explanation. You should also implement overlap between chunks. The last 100 tokens of one chunk should overlap with the first 100 tokens of the next chunk. This prevents information loss that happens at the boundaries. If a key concept is mentioned near a chunk boundary, it appears in multiple chunks, ensuring that the retrieval can find it regardless of where exactly it occurs in the text. Now, the 300 to 800 token range balances two competing goals. Smaller chunks increase the retrieval precision because they contain less potentially irrelevant information, but they lack the broader context. Larger chunks provide more context, but they reduce the precision because they contain more information that might not be directly relevant to the query. In production systems we have worked with, 300 to 800 tokens have proved to be the sweet spot, but your original optimal range might vary based on your document types and your query balance. I would recommend testing with your actual corpus to find what works best for your specific use case. Now let's talk about the metadata architecture, which enables intelligent filtering and ranking at the query time. Metadata should be the first class concern in your system design. Each chunk should carry contextual information about its origins. So the source document identifier, the hierarchical section information showing when the document this chunk appears, timestamp or version information for temporal filtering, and document type classification like API documentation versus support articles versus, for example, the blog post. This metadata supports pre-retrieval filtering, which is pretty powerful. Queries about recent features should reach filter by recency before even doing similarity search. Queries about API documentation should filter by document type. This approach reduces your search space before similarity computation happens, which improves both performance because you're searching fewer vectors and relevance because you're only looking at the appropriate content. Metadata also enables sophisticated ranking strategies that go beyond pure similarity scores. You can weight official documentation higher than the community contributed content. You can prioritize recent information over outdated content when recency matters. You can boost verified sources or user generated content based on your domain requirements. So most of the vector databases, they do support native metadata filtering, which enables efficient pre-filtering before similarity search even runs. You should store this metadata alongside your embeddings in the database. When designing a metadata schema, think carefully about your anticipated query patterns and what filtering requirements you'll have. The metadata schema should be driven by how users actually query your system. Now let's talk about the embedding generation strategy, which has significant implications for your both cost and performance. So embedding generation should be bashed for production efficiency. Individual API calls for each chunk introduce unnecessary latency and overhead that compounds at scale. Now let me give you some concrete numbers, but keep in mind that these costs change frequently, so you will need to check current pricing for a specific provider and model. For systems with 10 million chunks, embedding cost varies significantly by provider and model. At current pricing for typical models as of late 2024, you might expect one-time cost ranging from about $500 to $10,000 depending on your chunk size and which embedding model you choose. The wide range here reflects the fact that different providers charge very different rates. Some providers charge around 0.001 per 1000 tokens, while others charge 0.00 or even more. You'll need to calculate using your specific provider's rate sheet and your actual average chunk sizes. You should generate embeddings only for new content. When you're processing updates or new documents, don't re-embed the content you have already embedded. Storing the embedding model version with each vector so that you can track which model generated each embedding. This enables selective re-embedding when you upgrade models, rather than having to re-embed your entire corpus at once. One more important consideration. Vector dimensionality varies significantly by model. Common dimensions include 384, 768, 1024, 1536, or even 3072 or higher. You should choose based on your quality requirements balanced against your storage constraints. Higher dimensions generally provide better semantic representation quality, but they increase both storage cost and query computation cost. This is something you'll need to experiment with your specific use case. Now, let's walk through the three optimization strategies for production embedding generation that we have found effective. So, number one, you should batch aggressively with your provider's limit. You should send the maximum number of chunks per request while respecting the token limits and rate limits. This approach amortizes the fixed per request overhead across many chunks, which improves the throughput and reduces the costs. Every API call has some fixed overhead regardless of how much data you're sending, so batching lets you spread that overhead across more productive work. Now, number two, implementing embedding caching with model version tracking is pretty key. When you're processing updates or encountering duplicates, you should reuse the cached embedding rather than making new API calls. Store the model version alongside each cached embedding so you can selectively re-embed when you upgrade models. This eliminates redundant API calls completely, which can save substantial costs in systems where documents are frequently updated or reprocessed. So, number three, now invest in quality embeddings. This might seem counterintuitive because higher quality models offer cost more per API call, but here's a trade off that often makes sense. Better embeddings improve the retrieval precision, which means you can retrieve fewer chunks and still get accurate answers. Better retrieval also means fewer LLM calls because you're not regenerating the answers due to the poor initial retrieval. In production workloads with sufficient query volume, the upfront cost of quality embeddings is typically recovered through reduced downstream LLM costs. Let me give you a concrete example. If upgrading from a basic embedding model to a high quality one costs you let's say an extra $5,000 upfront, but it reduces your LLM cost by let's say 10% through better retrieval, and you're spending let's say 10,000 per month on LLM calls. You break even in 5 months and save money continuously after that. The exact economics depends on your specific volumes, but the principle generally, holds broadly. The key insight here is that embedding is a one-time cost per chunk, while LLM generation happens on every query. Optimizing for better retrieval quality through high quality embeddings often reduce the total cost of ownership in production systems. Now let's talk about vector database selection, which is a pretty critical architecture decision that you should spend a lot of time on. Vector database selection involves trade-offs between operational complexity and cost efficiency. There is no universal right answer here. It depends on a specific situation. Managed services handle all the infrastructure, scaling, and maintenance for you. This is particularly valuable if you have a small team or limited DevOps capacity, or you just have a very high functioning or very, very demanding roadmap in your organization. Prices vary significantly by cloud provider and region as well. Typically, you'll see starting prices around $25 to $100 per month for development workloads, scaling to thousands per month at production volumes. Now, I want to emphasize that these are rough ballpark figures and pricing changes pretty frequently. You will need to check current pricing for a specific cloud provider, region, and feature requirements. The self hosted options provide cost efficiency at scale and give you the full configuration control, but they do require a lot of DevOps expertise as well as investment. So you'll be handling deployment, scaling, backup, monitoring, and all the operational concerns yourself. Let's say if something breaks at 3 a.m. and you're the one who needs to fix it as a DRI on call, then you'll definitely prefer to have managed services. For let's say for teams with strong DevOps capabilities and high volumes and a lot of investment from the organization in terms of resources, in terms of people, then cost savings can be pretty substantial by self-hosting these vector databases and then also operationalizing them. So now your decisions should consider several factors. Query volume matters pretty significantly. If you're handling thousands of queries per second, the cost difference between managed and self-hosted becomes quite meaningful. So document count matters as well. At 10 million plus documents, managed service costs can become very high. And budget constraints, obviously they matter. And team capacity matters, team resources matters. So if you have a small team without a dedicated or DevOps resources, managed services often make more sense from a total cost perspective. When you factor the all of the engineering time, the developers' time, and more. For most teams, I would recommend starting with a managed service, and this lets you focus on building features and iterating on your product rather than managing database infrastructure. Once you exceed about 10 million documents or 1,000 queries per second, that's when you should evaluate whether the cost savings or self hosting justify the operational investment. At that scale, you'll likely have the team size and resources to manage the infrastructure effectively, so the trade off often shifts in favor of self hosting. Now, let me explain the internal architecture of vector databases so you understand how to optimize the performance for your specific requirements. Vector databases employ specialized indexes for efficient approximate nearest neighbor search. The most common approach is HNSW, which stands for Hierarchical Navigable Small World Graphs. HNSW builds the hierarchical graph structures that enable the logarithm like search complexity. Now, let me be precise about what this means in practice. For 10 million vectors, a brute force linear search would require 10 million distance calculations comparing your query vector to every single vector in the database. HNSW reduces this dramatically from, let's say, 10 million linear comparisons to typically hundreds of few thousand distance calculations, depending on your configuration parameters like EF underscore search and M. The exact number varies based on your index parameters, the dimensionality of your vectors, and your data distribution. But the key point here is that you're achieving orders of magnitude improvement over brute force while still maintaining the high recall quality. This gives you near logarithm search time in practice. For achieving the millisecond level latency at the 95th percentile, index structures should typically be memory resident or memory mapped with ample page cache. This is an important implementation detail. While the actual vector data can be stored on disk, the index structure of the graph that guides the search needs to be in memory to achieve those millisecond query times. This is why vector databases have significant memory requirements that scale with your corpus size. The query performance depends heavily on how you configure your index parameters. Increasing the number of connections in HNSW graph, which is the M parameter, improves the recall at the cost of requiring more memory. You will need to tune these parameters based on specific quality requirements, your hardware capabilities, and your latency SLAs. There is always a trade-off between memory usage, query speed, and recall quality. You will need to find the right balance for your specific requirements through load testing. One important note here is that please don't use default settings that are designed for demo datasets with thousands of vectors. Production settings for millions of vectors are quite different and they need careful tuning based on your actual hard workload and hardware. The storage layer can separate hot and cold data pretty effectively. You can keep recent documents in hot storage with index for fast access. Archived documents can move to cold storage with high latency but much more lower costs. This tiering strategy reduces your overall infrastructure cost while maintaining performance for the data that's frequently accessed. Now let's talk about the sharding strategy for scaling beyond the capacity of a single database instance. You'll want to consider sharding when you start seeing query latency exceed your SLAs or when you approach the resource limits on your database instances. Typical considerations begin around 10 million documents, though the exact threshold really depends on your vector dimensionality, your queries per second, and your hardware specifications and your index configuration. In my experience working with the production systems, some handle 20 million documents pretty comfortably on a single instance with powerful hardware and relatively low query rates. Others, however, need to shard much earlier when they're handling thousands of queries per second. Date-based sharding works particularly well for time-sensitive content. You would put recent documents in hot shards and historical documents in cold shards. Here's why this approach is pretty effective. When users query about recent information, you search only the recent shards, which reduces both latency and resource consumption. You're not wasting cycles searching through the historical data that couldn't possibly have answer. The query router should analyze the queries and metadata filters to determine which shard is to target. Queries with temporal components can route to specific time ranges. Broad queries without temporal filters might need to query all shards in parallel, merging the results afterwards, though this is much more expensive. As a starting point, I would recommend targeting a few million vectors per shard and validating this with load testing under realistic query patterns. Optimal shard size really varies by a specific workload characteristics. There is no universal maximum. You will need to run realistic load tests with your actual query patterns to find the right shard size for your system. And the nice thing about this architecture is that it scales linearly. Doubling your shards roughly doubles your capacity here. This linear scaling property makes capacity planning straightforward as you grow. Now let's talk about hybrid search, which combines complementary retrieval approaches to improve the overall quality. Hybrid search combines dense vector search for semantic similarity with sparse keyword search for lexical matching. These two approaches have complementary strengths that work well together. Vector search excels at semantic understanding. It can match queries to documents that have similar meaning even when they use completely different terminology. This is the power that got everyone excited about the embedding based search. Keyword search, on the other hand, excels at exact matching. It reliably finds the specific identifiers, error codes, or technical terms that may not embed with high signal strength. The hybrid strategy should retrieve the top 100 candidates from both systems in parallel. You run both searches concurrently to minimize the latency, and then you use the reciprocal rank fusion to merge the results. And this is pretty important. Reciprocal rank fusion works by combining rankings based on position rather than trying to normalize the absolute scores, which is valuable because vector search scores and keyword search scores operate on completely different scales and are not directly comparable. After merging, you would deduplicate to remove the chunks that appears in both result sets. Then these merged candidates proceed to the re-ranking. This approach can improve the recall from approximately 60% to 85 to 90% in systems where both semantic and lexical matching contribute to the relevance. Now, I want to emphasize that these performance gains vary significantly by corpus characteristics and query patterns. If your queries are purely semantic in nature, you might not see much benefit from adding keyword search. If your queries are all exact matches, then you might not need the vector search at all. But for most production systems that handle diverse query types, hybrid search provides a meaningful quality improvement. The cost of this approach is pretty minimal from a latency perspective. Running both searches in parallel means your total time equals a maximum of two searches rather than their sum. And the improved recall typically means better answers, which often means fewer retries and lower overall system costs because the users get the right answer on their first query. Now, let me show you how to implement the hybrid search in practice. The implementation here should retrieve both the systems concurrently using promise.all. Vector search returns candidates based on embedding similarity, and keyword search returns candidates based on BM25 scoring, which is standard probabilistic ranking algorithm for keyword search. Now, here's where reciprocal rank fusion comes in. Instead of trying to normalize the scores from two completely different systems, which is problematic because they are on totally different scales, reciprocal rank fusion combines the rankings based on the positions in the results list. It is robust across different scoring systems and does not require any parameter tuning, which makes it ideal for production use where you want reliability. Then we deduplicate by chunk ID because the same chunk might appear in both result sets. When a chunk appears in both vector and keyword results, that's actually a strong signal that it's highly relevant. It's matching both semantically and lexically. We just don't want to send it to the re-ranker twice, so we keep it once with this combined ranking signal. Now I want to add an important note here that about this code. This is simplified for illustration purposes. Production implementations require comprehensive error handling so failures don't crash your system, timeout management so queries don't hang for a very long time, circuit breakers to handle downstream service failures gracefully, and detailed monitoring so that you know when something is not working correctly. So please don't deploy this exact code to production without adding all those operational concerns that I just mentioned. The key implementation detail is parallel execution. If you were to run vector search first and then keyword search sequentially, you would add their latencies together. By running them in parallel, your total time is just the maximum of the two, which is typically the vector search time since it's usually a bit slower than the keyword search. Now let's talk about the re-ranking, which provides the final refinement of your candidate selection. Re-ranking typically improves the retrieval quality by 20 to 30% over your initial retrieval. though I want to emphasize that this depends significantly on your baseline retrieval quality and your specific corpus characteristics. If your initial retrieval is already excellent because you have well structured documents and like high quality embeddings, you might see gains in the range of 10 to 15%. If your initial retrieval is weaker, you might see larger improvements, potentially 40% or more. The exact improvement is highly dependent on your specific system. Cross-encoder re-rankers work differently from the bi-encoded embeddings we use for initial retrieval. They process the query and document as a joint pair, scoring the relevance together. Let me explain why this is more accurate. Bi-encoders models which generate embeddings process the query and documents independently. They never see them together. The model generates an embedding for your query, generates embeddings for your documents, and then you compare those embeddings using cosine similarity or dot product. Cross-encoder models take a fundamentally different approach. They process the query and document as a single combined input, which allows the model to directly access how well the document answers to the specific query. It can see the relationship between words in the query and words in the document clearly. For production systems, you should use cross-encoder models that have been fine-tuned specifically for on-question answering data. These models are trained explicitly to score query document relevance, which makes them far more accurate than general-purpose models for this specific task of determining relevance. Now, re-ranking does add approximately 200 to 300 milliseconds of latency because cross-encoders are computationally expensive. They are processing much more information than bi-encoders. But for applications where answer quality directly impacts user satisfaction, this trade-off often proves to be pretty worth it. Better answers lead to happier users, fewer support escalations, and higher engagement rates. The pipeline narrows efficiently at each stage. Your initial retrieval reduces millions of documents down to 100 candidates using fast approximate search. Re-ranking then carefully refines these 100 candidates to the final top 10 using the more expensive but more accurate cross-encoder scoring. Now let's talk about the context assembly, which requires managing token budgets while maximizing the information value you're providing to the LLM. After re-ranking yields your top 10 most relevant chunks, context assembly manages how you present this information to the LLM. Your target context size should depend on your model capabilities. For models with 16,000 to 32,000 token context windows, which were pretty common until recently, you would typically target 4,000 to 8,000 tokens of retrieve context. Newer models with, let's say, 100,000 plus token windows, you know, or like for example GPT-4 Turbo with 128k tokens or Claude with 200k tokens, allows for much larger context. But here's something that is very important to understand. More context doesn't always improve quality. Excess context can actually dilute real relevance. If you send 50,000 tokens of context to the LLM, it might struggle to identify the most relevant information among all that text. There is research showing that retrieval quality often matters much more than sheer context size. So even with these large context windows available, I would recommend starting with a major context budget. Assemble chunks in descending relevance order. Start with your highest rated chunk and add subsequent chunks until you're approaching your token budget. Include the metadata with each chunk to enable source attribution and proper citations. You should format chunks pretty clearly. Something like, let's say, document, API reference.md, section, authentication, content, and then chunk text. This clear structure helps the model understand where information is coming from and enables it to generate accurate citations. The LLM can, say, for example, according to the API reference documentation, instead of just generating information without any attribution. Now, one more consideration for production systems. You might want to implement diversity constraints to reduce redundancy. If your re-ranking returns, let's say, three chunks from the same document section that all essentially says the same thing, you're essentially wasting tokens. Consider deduplicating or selecting more diverse sources to maximize the information value per token you're sending. And here's something to think about for the edge cases. Sometimes your retrieval won't find chunks that are highly relevant. All your similarity scores might be mediocre. In these cases, you'll need a fallback strategy. Maybe you return a response saying, I don't have enough information to answer that confidently, rather than just forcing the LLM to generate an answer from weak context. This maintains answers quality and users trust better than generating low quality answers that based on marginally relevant context. Now let's talk about the LLM integration and how to structure this for production reliability. The LLM integration layer constructs your prompt from three different distinct components. So number one, the system prompt defines the behavior and constraints. Number two, the retrieve context contains the relevant chunks you have assembled. And number three, the user query is the actual question being asked. The system prompt should be critical for controlling the LLM behavior. It establishes operational boundaries by instructing the LLM to answer based on provided context rather than its training data, which might be outdated or incorrect for a domain. It tells the LLM to cite sources by document name, which is pretty essential for building user trust. And it instructs the LLM to acknowledge when context doesn't contain sufficient information rather than making things up. You should use streaming messages for better perceived performance. Users see word appearing immediately rather than waiting to complete the generation, which might even take 10 to 15 seconds for a long response. This makes the system much more responsive, even though the actual total time to complete the generation is same. In user experience terms, time to the first token matters significantly more than the total completion time for perceived responsiveness. Streaming also enables early termination, which is important for cost control. If a user closes the connection or asks a new question before the current answer completes, you can stop generating token immediately. Since you can only pay for tokens actually generated, this can save meaningful cost if users frequently interrupt or abandon queries. For production systems, you should implement retry logic with exponential backoff for API failures. LLM APIs occasionally fail due to rate limits, temporary service issues, or even network problems. This happens more frequently than you might expect. Your system should handle these failures gracefully with retries that back up exponentially. If the retries ultimately fail, fall back to cache responses when available rather than showing a hard error to the user. If you have a cache response from a very similar previous query, searching that is better than telling the user that system is completely down. One more thing to keep in mind here. There is a cold start period when you first launch your system. Before you have built your cache responses, all your queries will go through this full pipeline and will be slower. This is pretty normal and expected. Your performance will improve substantially as your cache warms up over the first few hours or days of the operation. Now let me show you how to structure prompts effectively for RAG systems because this really does make a significant difference in production quality. The prompt emblem should provide clear information organization for the LLM. The system prompt establishes rules and behavioral expectations pretty upfront. It tells the LLM exactly what you expect, answer only the provided context, cite sources properly, acknowledge when you don't have sufficient information, and be concise while remaining complete. The context section should present retrieved chunks with clear delimiters. Each chunk should be separated with a visible marker like three dashes. Each chunk should include its source document name so the LLM can cite it properly, and the content should be clearly labeled. This structure isn't just aesthetic, it generally helps the LLM parse and understand the information structure it's working with. The user query should appear at the end after all the context has been provided. This ordering matters from a cognitive perspective. If you put the query first, the LLM might start formulating an answer before it's fully processed all the available context. By putting the query last, the LLM has absorbed all the available information before it begins generating an answer. This follows a natural flow of reading and understanding before answering. Clear structure dramatically improves answer quality in production. The LLM understands exactly what information is available and where it comes from. This reduces hallucination because the LLM sees explicit boundaries around this knowledge. It knows these chunks represent all the information it has. If the answer is not in these chunks, you should acknowledge that rather than making something up. The rules in your system prompt are critical for controlling behavior. Instructing the LLM to only use provided context prevents it from generating answers based on its training data, which might be outdated or incorrect for a specific domain. Requiring citations make answers verifiable and it builds users' trust significantly. When users can see where information comes from, they are much more likely to trust and act on the answer. Now, here's something important. You should A/B test different prompt formulations to optimize for your specific use case and document types. And what works beautifully for your API documentation might not work as well as for customer support tickets. The tone, structure, and specific instructions might need adjustment. I recommend setting up experiments where you test different prompt variations on your golden dataset and measure which produces better answers according to your quality metrics. Prompt engineering is still more art than science, so systematic experimentation is essential for finding what works best for your domain. Now let's talk about multi-layer caching strategy. This provides the highest leverage optimization for both cost and latency in production systems. Caching should be the most important production optimization that you implement. Well designed caching can reduce costs by up to 70 to 80% in FAQ style systems where users frequently ask similar questions. But I want to be very clear about when you will see these kind of results. If your application is something like a customer support bot where many users ask like what's your return policy or how do I reset my password, you'll see extremely high cache hit rates potentially reaching to 70 to 90%. However, if your queries are pretty unique each time, like in research applications where users are just exploring novel questions that haven't been asked before, your hit rate might only be 10 to 20%, and the savings would be proportionally lower. Understanding your query distribution is pretty critical for setting realistic expectations about caching benefits. You should implement three complementary cache layers that work together. So, number one, query cache store complete responses for identical queries. This is your first line of defense and your fastest path. Number two, embedding cache store query embeddings for repeated query text. This saves on embedding API costs. And number three, retrieval cache stores retrieve candidates for semantically similar queries. This is the most sophisticated layer and requires careful implementation. So let me explain why each layer matters. Query cache has the highest hit rate for workloads with exactly repeated queries. If 100 users ask exactly what is your return policy, and in the same day you generate the answer once and serve 99 cache responses. This saves 99 LLM API calls, 99 retrieve operations, 99 embedding generations. The cost savings compound across every component you skip. Embedding cache saves on your embedding API. Instead of generating a new embedding for every single query, you cache query embeddings. For queries and their exact textual variants that you have seen before, this eliminates embedding API calls entirely. While individual embedding calls are relatively cheap, they do add up significantly at scale. Now, retrieval cache is much more sophisticated and it requires careful implementation. It caches the top 100 retrieved candidates for semantically similar queries. If two users ask how to reset password and how do I reset my password, these are semantically similar even though the text differs. The retrieval results should be nearly identical. By caching retrieval results with semantically similarity matching above some threshold, you can skip the expensive vector research for similar queries. But implementing this correctly is tricky. You need a fast way to determine if any new query is similar to a cached one without doing the full expensive similarity search you're trying to avoid. Often, this is implemented with a smaller, faster model or a keyword based approximate matcher that's much more cheaper than a full vector search. Now, here's a critical consideration for production systems. When you do update documents, you need a strategy for invalidating related cache responses. You absolutely cannot serve cache responses about your old return policy after you have updated it. Use content based cache keys that include document version hashes or implement a cache invalidation system that tracks which documents contribute to which cache responses. This is essential for maintaining correctness over time. Together, these three cache layers create a cascade that can eliminate 60 to 80% of expensive operations in systems with the right query patterns. Query cache catches exact matches, embedding cache catches queries you have embedded before, and retrieval cache catches semantically similar queries. Between them, they can dramatically reduce your operational costs. Now, let me walk you through how to implement this caching system in practice. The implementation should check each cache layer sequentially, short circuiting as soon as you find a hit. First, you hash the query to create a cache key and check the query cache for an exact match. If you do find an entry, you return it immediately. This path has sub 10 millisecond latency and should handle the bulk of your repeated queries. If the query cache misses, you check the embedding cache. If you have embedded this exact query text before, you retrieve the cache embedding and skip the embedding API call. This saves approximately 50 milliseconds of latency and the API cost. If the embedding cache misses as well, you generate a new embedding and store it with the 24-hour TTL. The TTL ensures that your embedding models are updated or API pricing changes, old cache embeddings eventually expire and regenerate. Future queries with analytical text can reuse this embedding. After you complete retrieval and LLM generation, you store the complete response and query cache with a 1 hour time to live. The TTL here is important for maintaining freshness. If your document corpus updates, stale responses should eventually expire and regenerate with the new information. 1 hour is a reasonable balance for most systems, but you might want shorter TTLs if your content updates pretty frequently, or longer TTLs if your content is quite stable and rarely changes. Cache hit rates vary significantly by workload characteristics. In production systems we have worked with, we typically see 40 to 60% hit rates for general question answering applications. For FAQ systems where users repeatedly ask the same questions, hit rate can reach up to 80 to 90%. But for research heavy applications where almost every query is unique, hit rates might only be 10 to 20%. You should monitor your actual hit rates in production and adjust your caching strategy accordingly. If you're seeing very low hit rates, you might need to implement semantic caching or adjust your TTL settings. The implementation typically uses standard caching libraries. Redis is a very popular choice because it's fast, supports TTLs natively, and can be shared across multiple application servers. This means all your servers benefit from the same cache responses rather than each server maintaining their own isolated cache. The code here is pretty straightforward. Check cache, if missed, then compute and store, and then return result. Now, one practical note about the implementation that's pretty important. Please make sure that you handle cache failures gracefully. If Redis goes down or it becomes unavailable, your application should still work, just slower because it's computing everything fresh without cache benefits. Don't let cache failures take down your entire system. There's a common production problem that is easy to avoid with proper error handling. Now let's talk about the cost optimization framework, which is essential for building economically sustainable rack systems. Cost optimization should be a systematic practice for production rack systems because without careful optimization, costs can become pretty high. In some systems we have analyzed, an unoptimized cost could reach up to $30,000 per month for moderate traffic levels. With strategic optimization, similar loads can operate at $5,000 to $8,000 per month. The exact numbers depend entirely on your specific volumes and characteristics, but the principle holds broadly. Optimization is essential for sustainability. LLM API calls typically represent 60 to 80% of your total spending. You need to calculate your per query cost based on a specific model pricing, your average context size, and your typical response length. As a rough example using current pricing, if you're using a model that costs $0.01 per 1000 tokens with average requests containing 10,000 context tokens plus 2,000 completion tokens, each query costs approximately $0.12 in LLM fees alone. At 1000 queries per day, that's $3,600 per month just for LLM costs, not counting your infrastructure, embeddings, or other costs. These numbers change frequently as providers adjust pricing, so always check current rate sheets for your planning. Here's how we approach optimization in production. Aggressive caching can reduce LLM calls by 70% in workloads with sufficient query repetition. With a 70% cache hit rate, you only make 300 LLM calls per day instead of 1000. This brings your LLM cost down to around $1,100 per month from $3,600. That's a pretty dramatic reduction. Context optimization limits context only to necessary chunks, reducing token usage. Instead of always sending 10 chunks totaling 10,000 tokens, evaluate whether 5 chunks with 5,000 tokens would be sufficient for good answer quality. This reduces per query cost significantly. But please be careful here. Sending too little context would hurt answer quality, so you need to find the right balance through systematic experimentation. Implementing a model router that directs simple queries to smaller, cheaper models while routing complex queries to larger, more capable models optimizes your costs versus quality trade off. If a query is straightforward with clear context, you might want to use a model that costs half as much. Route only the complex queries requiring sophisticated reasoning to your larger, more expensive models. The router itself can be a simple classifier or even another smaller LLM call, which is cheap compared to the savings you achieve. You should monitor your cost per query metric pretty regularly in production. If it exceeds $0.05, you probably need better optimization strategies. A typical target is $0.02 or $0.03 per query for sustainable economics at scale, though this varies by your application's value proposition as well. If each query drives high value transactions, you can obviously afford higher per query costs. Now, tracking costs by component, embeddings, retrieval, re-ranking, and generation. Detailed cost observability identifies optimization opportunities you might otherwise miss. Maybe your re-ranking costs are higher than expected, or maybe embedding costs could be reduced through better caching. You can't optimize what you don't measure in detail. Now let's talk about the monitoring architecture, which is essential for maintaining production quality and catching issues before they impact the system. Production RAG systems require comprehensive observability across three dimensions, and you simply cannot optimize what you don't measure. Says how well your system is answering questions. So number one, answer elements tracked through user feedback mechanisms like thumbs up or thumbs down buttons. This is your most direct signal of user satisfaction. Number two, retrieval accuracy measured by evaluating whether retrieved chunks actually contain the information needed to answer the query. You can evaluate this by automatically using your golden dataset. Number three, user satisfaction signals monitored through follow-up question patterns, conversion abandonment rates, and support ticket escalation rates. If your users are frequently asking follow-up questions, your initial answers might not be comprehensive enough. Performance metrics track system health and operational reliability. So number one, query latency should target sub 3 seconds end-to-end P95 percentile of queries in most applications. But let me be specific about what this means. That's time to first token with streaming, not completion time. Users perceive time to first token as system responsiveness, which is what matters for users' experience. Number two, cache hit rate should exceed 40% for general systems and 70% for FAQ style systems. Lower hit rates indicate either caching implementation issues or unusual query patterns worth investigating. And number three, error rate should stay under 1% of all queries. Any increase in error rate indicates problems requiring immediate investigation. 1% might sound low, but for a system handling thousands of queries daily, that's still dozens of failed requests frustrating users. Cost metrics prevents budget overruns and enables systematic optimization. Number one, cost per query is a fundamental economic metric. Track it daily and set up alerts if it spikes pretty unexpectedly. Number two, LLM token usage broken down by prop tokens and completion tokens. This breakdown shows where tokens are being spent and help identify optimization opportunities. Maybe your prompts are larger than necessary, or maybe responses are longer than they need to be. And number three is embedding API call volume to identify opportunities for better caching or more efficient batching. You should set up alerting on all these critical metrics. If a query latency spikes above 5 seconds, you should get alerted immediately so you can investigate. If cost per query doubles suddenly, that might indicate a problem with your caching layer or an API pricing change that you might not be aware of. If error rate climbs above 2%, you have a production issue that needs immediate attention before it affects more users. Without comprehensive monitoring, you're essentially flying blind. You don't know whether changes you make improve or degrade quality. You don't know when cost spikes without unexpectedly. And you don't know when performance degrades until users start complaining and filing support tickets. Invest in solid monitoring infrastructure from day one. It's not optional for systems that you're running in production, it's an absolute must. So now let's talk about quality evaluation pipeline, which requires systematic automated testing that you can run continuously. Quality evaluation requires systematic testing, not just occasionally checking a few queries manually and assuming everything is fine. You need a structural evaluation pipeline that runs automatically and catches issues before they reach users. You should create a golden data set of 100 to 500 representative queries covering the full range of user questions. This dataset should include easy queries with clear answers that test basic functionality, complex queries requiring multi-hop reasoning, ambiguous queries that might have multiple valid interpretations, and queries where your corpus simply does not have good information. This diversity ensures that you're testing the full range of system behavior, not just the happy path. Now run your RAG system on these queries and evaluate both retrieval quality and generation quality separately. This separation is valuable because it helps you diagnose where the issues are occurring in your pipeline. For retrieval, you should measure your precision, which is the percentage of retrieved chunks that are actually relevant to the query. You should measure the recall, which is the percentage of all relevant chunks in your entire corpus that you successfully retrieved. And you can calculate NDCG, which stands for Normalized Discounted Cumulative Gain. This metric measures ranking quality and penalizes situations where relevant documents rank too low. If a highly relevant document ranks 50th instead of 5th, first, NDCG penalizes that more heavily. For generation quality, you should measure answer correctness by comparing generated answers to expected answers or answer characteristics. You can leverage modern LLM as a judge frameworks where you use language models to score response quality. Tools like RAGAS or ARES and TrueLens can automate evaluation at scale without requiring extensive human labeling for every single query. This makes continuous evaluation much more practical for production systems. You should measure faithfulness by checking whether the answer only uses information from retrieved context or whether it hallucinates information that's not provided in the chunks. And you should measure relevance by evaluating whether the answer actually addresses the user's question or it's actually off topic. You should also integrate this evaluation pipeline into your CI/CD system. Every code change should be evaluated against your golden data set before it's allowed to deploy. If metrics degrade below your thresholds, for example, if retrieval precision drops below 75% or answer correctness drops below 80%, you should automatically block the deployment and trigger the investigation into what changed. This catches regressions before they reach the productions and impact real users. Target metrics vary by domain and your specific application requirements. Typical production systems target 75 to 85% retrieval precision, 65 to 75% retrieval recall, and 80 to 90% answer correctness. But you should adjust these thresholds based on your specific quality requirements and what's actually achievable with your corpus. Some domains with very clean, well structured documentation might achieve higher scores. Others with messy, unstructured content might have lower realistic ceiling scores. The key here is understanding that your baseline and you're tracking trends over time. So now track these metrics over time and look for trends. A slow, gradual degradation in quality might indicate issues with document quality as new content is added. Model drift as user behavior changes, or corpus growth causing retrieval to become less precise as you scale. Now let me show you the complete production architecture that ties all these components together into a cohesive system. The production architecture should enable horizontal scaling to handle thousands of concurrent queries reliably. Multiple API servers sit behind a load balancer which distributes incoming requests throughout the servers. This provides redundancy so if one server fails, others continue serving traffic without interruption. It also scales your compute capacity. When you need more throughput, you simply add more API servers. The Redis cache layer provides fast query cache lookups with typically sub 10 millisecond response times. Importantly, this cache should be shared across all API servers so cache hit benefits every server. If server 1 computes an answer and server 2 can immediately serve it from the shared cache. Using a distributed cache architecture means your cache hit rate compounds across all servers rather than each server maintaining its own isolated cache with lower effective hit rates. Each vector database shard should employ a primary-replica topology. The primary handles writes when a new document is added to the system. The replica handles read queries, which represent the vast majority of operations in RAG systems since you're reading far more than writing. This topology provides fault tolerance. If primary fails, a replica can be promoted to primary automatically. It also distributes a read load across multiple replicas. With 3 replicas, you can handle roughly 3 times the read query throughput. Circuit breakers protect against cascading failures when external servicing might be experiencing issues. If the LLM API is responding slowly or timing out, circuit breakers can fail fast and return the cached responses or clear error messages instead of hanging out indefinitely and consuming resources. This graceful degradation is essential for maintaining overall system stability under adverse conditions. Centralized monitoring aggregates metrics from all your services, provides comprehensive system visibility through unified dashboards. You can quickly identify which component is causing issues when problems arise rather than hunting through logs across multiple services. This architecture typically handles 1,000 concurrent queries with 95th per percentile latency under 3 seconds in production deployments we have worked with. But actual performance depends heavily on your specific hardware, your configuration choices, and your query complexity characteristics. You will need to run comprehensive load tests with your actual query patterns to validate performance for your specific requirements. Now let's talk about scaling beyond 10 million documents, which often requires much more sophisticated sharding strategies. Scaling beyond 10 million documents often benefits from type-based sharding beyond simple date-based approaches. The idea is to separate different document types into dedicated clusters. API documentation goes to one cluster of shards, support content goes to another cluster. Blog post or general content goes to the third cluster. This separation provides two substantial benefits. Number one, improve performance. When a user asks an API question like, how do I authenticate with an API? You only query the API documentation cluster. You don't waste computational resources searching through support tickets or blog posts that couldn't possibly contain API documentation. This typically reduces query latency significantly compared to searching everything, though the exact improvement depends on how well your query aligns with your sharding strategy and how much faster the small targeted search is. Number two is improve relevance. By focusing the search on the current document type, you improve the retrieval precision. You're not mixing API documentation with marketing blog posts in your results. The LLM receives context that's all from the same authoritative source type, which tends to produce better, more consistent answers. The query router should employ a classifier to detect query intent based on keywords and patterns. The classifier looks for signals about what type of information that the user is seeking. If the query mentions API, endpoint, authentication, or integration, then we route it to API documentation. If it mentions keywords like error, issue, problem, or broken, we route it to support ticket content. If it's more general or asks about high-level concepts, we may be routed to blog post or general documentation. For ambiguous queries where the intent is not clear, you query multiple clusters in parallel and merge the results. This ensures that you don't miss relevant information when query type is uncertain. The latency of parallel queries is just the maximum of all clusters queried, not the sum, so it's not as expensive as sequential searching. Each cluster should be independently scalable based on the actual usage patterns. Your API documentation cluster might need significantly more resources than your blog post cluster if API queries are far more frequent in your user base. This allows you to optimize resource allocation based on real demand rather than treating all document types equally. At 100 million documents, expect the infrastructure costs of approximately 15,000 to 25,000 monthly, including the vector databases, computing and compute instances, and LLM API costs. But I want to empathize that actual costs vary significantly based on your query volume, how effectively your caching strategies are, your hardware choices, and your specific cloud provider pricing. This is a rough ballpark figure to help you plan, not a precise estimate that you should rely on without doing, your own detailed cost modeling. Now let's talk about the production deployment checklist you should complete before going live with real user traffic. Before deploying to production, you should verify that several critical components are ready and thoroughly tested. Let me walk you through each one because skipping any of them would lead to production incidents. So, number one, document processing pipeline capable of handling your volume. Calculate your expected processing time based on your throughput budget for parsing, tokenization, and embedding API limits. Consider rate limits carefully, your concurrent processing capacity, and comprehensive error handling. If your embedding API allows 1,000 requests per minute and you're batching 100 chunks per request, you can process 100k chunks per minute under ideal conditions, so 10 million chunks would take around roughly 100 minutes. but add buffer time for errors, retries, and rate limit backoff. Number 2, vector database configured with production approximate index parameters. So don't use default settings that are meant for demo datasets which are ideal for thousands of vectors. Test query performance under expected load through realistic load testing. Simulate 1,000 concurrent queries with your actual query patterns and measure latency distributions carefully. Identify the bottlenecks before they impact real users. Number 3, caching layer implemented and thoroughly tested in staging. Verify that cache hit rate meets your expectations before production deployment. If you're expecting 60% cache hit rates but you're only seeing 20% in staging, investigate why before going live. The expected cost savings won't materialize if your cache hit rates are substantially lower than planned. Number 4, monitoring and alerting configured for quality, performance, and cost metrics. You should set thresholds based on your SLAs. You should not wait until the production is set up for monitoring. You need these systems operational from day one so you can detect issues immediately when they occur. Number 5, evaluation pipeline with automated regression testing. Maintain your golden data set and run evaluations daily or even hourly. This catches bugs and performance degradation before users notice widespread issues and they start filing support requests. Setup alerts and evaluation scores drop below your quality thresholds. Number 6, comprehensive failure handling, including rate limiting, circuit breakers, and graceful degradation. Test these failure scenarios extensively in staging, simulate the LLM API being completely down, and verify a system degrades gracefully instead of totally crashing. Simulate high load to verify rate limiting works correctly. Simulate slow responses to verify timeouts, and circuit breakers activate appropriately. Number 7, cost tracking dashboards showing real-time breakdown by component with budget alerts. You should know at any moment whether you are within budget and where your costs are coming from. Set up alerts if daily costs exceed expected thresholds so you can catch cost spikes immediately rather than discovering them at the month end. Without these components properly in place, you're not really ready for production traffic. We have seen too many teams rush to production without adequate monitoring or error handling, and it ends very badly in terms of incidents or high costs. Take the time to implement these properly before launch. And quickly, this will help you quickly diagnose any issues that may happen in production before your users notice it. Now, let me summarize the foundational architecture principles that should guide your implementation. So, number 1, you should use structure aware recursive chunking that maintains semantic coherence. This typically improves retrieval quality by 20 to 30% compared to fixed size approaches, though the exact improvement depends on your corpus characteristics. Your chunks should respect paragraphs, code blocks, and natural document boundaries that authors have intentionally created. Number 2, implement hybrid search combining vector similarity with keyword matching. This catches both semantic matches and lexical exact matches, improving the recall in systems where both type of matching matters. Typical improvements move around from 60% recall to 85 to 90% in diverse query workloads. Add re-ranking with cross-encoder models to refine your candidate selection. This typically provides 20 to 30% quality improvement over initial retrieval depending on your baseline quality. The latency cost of 200 to 300 milliseconds often proves worthwhile in applications where answer quality directly impacts user satisfaction and engagement. Number 4, build multi-layer caching with query cache, embedding cache, and retrieval cache. This can reduce your cost by 70 to 80% in FAQ style workloads with repetitive query patterns while improving latency significantly. Even in systems with more unique queries, caching still provides substantial benefits through the embedding and retrieval layers. Number 5, plan your sharding strategy for scale. Consider sharding when you start approaching 10 million plus documents or when query latency begins exceeding your SLAs. The exact threshold depends significantly on your queries per second, your vector dimensionality, your hardware specifications, and your index configuration. Having a plan, even if you don't need it, yet makes scaling much more smoother when the time comes. So number 6, monitor quality, performance, and cost continuously. Track detailed metrics and establish alerting on regressions, cost per query, cache hit rates, answer relevance, and query latency should all be monitored continuously from day one. Now, I want to emphasize one final time that performance characteristics vary significantly by your configuration, your hardware, your corpus characteristics, and your specific query patterns. The numbers I have shared today are typical ranges we have observed in production systems, but your actual mileage may vary. Test systematically with your specific workload and tune accordingly. There is no one size fits all configuration. Every system has unique characteristics that require careful tuning and optimization.